In the last class, I introduced this new quantity called the KL divergence. So given any pair of distributions P and Q, the KL divergence is basically this quantity summation over all x, P of x log P of x by Q of x. Another way of writing this is, which is sometimes convenient, is the form. You can say that this is expectation with respect to Px of log P of x by Q of x, and it can also be written in a slightly more convenient form as the expectation with respect to Q of x of P by Q log P of x by Q of x. And this form is particularly helpful. We saw use of this particular form of the KL divergence in that this is expectation of some function which is of the form y log y, which we know is convex, right? And that allows us to prove very useful properties of the KL divergence. In fact, this can be generalized. You can replace this y log y with any convex function, in fact, and you get what is called an F divergence. So if you replace this expectation with respect to Q of x of some function f of P of x by Q of x, then you get what is called an F divergence. And the KL divergence is a specific instance of the F divergence. The KL divergence is particularly important for us because we saw that the KL divergence is the excess rate or the penalty that you need to pay when you want to compress a source optimally, but then you don't know the true distribution. So if you compress the source with respect to a distribution Q of x, when the true distribution is actually P of x, then the best possible compression rate that you can get is essentially the entropy plus a penalty which is equal to the KL divergence. All right. And we saw that what we proved in the last class was that the KL divergence is always non-negative for any P and Q. And an important property is that this divergence is not a true metric, it's not a real distance, because the KL divergence is not symmetric. All right. All right, great. So in today's class, we'll continue this discussion on properties of entropy and the KL divergence. I'll also introduce a new quantity called the mutual information. I won't really stress upon the operational meaning of mutual information in today's class. We'll see where mutual information naturally arises, both in lossy source coding as well as channel coding later on. But we'll just introduce some of these notions and see some of the basic properties that these quantities have. All right. So before we proceed, we saw that the KL divergence is non-negative, but using an essentially identical approach, you can prove the following result, which is called the log sum inequality. And the log sum inequality basically says the following. Suppose I have two collections of numbers, or in other words, two vectors. Let's say I have alpha 1 up to alpha n and beta 1 up to beta n, and all of these alpha I and beta I are greater than or equal to 0. And this has the property that for any I for which I such that alpha I is equal to 0, I also have beta I is equal to 0. Okay. So if I have any collection of numbers, note that alpha and beta need not form probability mass functions. They just have to be non-negative. Then summation over all I, alpha I log alpha I by beta I, this is greater than or equal to summation overall I alpha I log of sum overall I alpha I divided by sum overall I of beta I. So the log sum inequality basically says that the sum of this alpha log alpha by beta quantity is greater than or equal to the same quantity but with the summation taken inside. All right. And we see that this automatically implies that the KL divergence is non-negative, because if alpha and beta are probability mass functions, then sum overall I of alpha I and sum overall I of beta I, they are both equal to 1. So the right hand side just becomes 0. All right. So this is a generalization of the fact that the KL divergence is non-negative. And it's very easy to prove this because we've already seen the previous thing. Essentially, the idea is just this. You multiply and divide each of these by summation alpha I. All right. So you take alpha I by sum overall j, alpha j, and this alpha I by sum overall j, alpha j, and so on, so that you convert them to probability mass functions. You get an additional term because now you have another summation overall I alpha I. And you can just take that outside, and effectively what you get is just 0 plus this particular quantity. Okay. It's not too hard. I would just encourage you to try it out yourself. It's just a simple exercise. Okay. Great. So after we saw that the KL divergence is non-negative, we use that property to derive some more interesting results. Firstly, we showed that if x is a random variable over a finite alphabet, then the entropy is less than or equal to log cardinality of x. Right? Or in other words, the entropy is maximized when the distribution is uniform for a given alphabet. Now this doesn't, we can't make a statement like this when the alphabet is infinite. So for that we derived another result which said that if x is distributed over the natural numbers, then and the mean is fixed, it's equal to mu, then the entropy of the random variable is always upper bounded by mu times the binary entropy of 1 by mu. Right? And I'd given an exercise that if I choose a distribution Q to be the geometric distribution, so Qx of I is equal to alpha times 1 minus alpha whole raised to I minus 1, then the mean is equal to 1 by alpha. What is the entropy equal to?
Minus log of alpha by 1 minus alpha plus.
So can you slow down?
Minus of
Minus
log of alpha by 1 minus alpha.
Alpha by 1 minus alpha.
Plus 1 minus alpha whole square.
1 minus alpha the whole
Log
square.
of 1 minus alpha. That minus is for every term. I got this term in it.
Okay. Are you sure there's a 1 minus alpha the whole square? You can just double check, but maybe effectively what you should get is that the entropy is 1 by alpha times the binary entropy of alpha, which should be equal to log or whatever minus log alpha minus 1 minus alpha by alpha log 1 minus alpha, right? Let's see if log 1 minus alpha. So this would be log alpha minus log alpha by 1 minus alpha minus 1 times log 1 minus alpha. It seems to be a bit different, so you can just double check. All right. But so that aside, we can also extend this to, so this was for random variables over the set of natural numbers, right? You can also prove something similar. So suppose that x is a random variable which is distributed over the whole numbers, so natural numbers and 0 potentially. A random variable over 0, 1, 2, 3 and so on. And just as before, the expected value of x is equal to the mean. Then the expected value of, the entropy of x is upper bounded by 1 plus mu times the binary entropy of 1 over 1 plus mu. Again, the proof is essentially identical to what we did earlier, but you have to be just a little more careful because now the random variable is also allowed to take the value 0. Okay. All right. So now that we have this, what I want to now do is use this to prove the lower bound that we had on the expected length of the optimal code. Okay, so if you recall, let's go back. Yeah. So recall that the optimal compression scheme was one where you sorted all of the sequences in decreasing order of probability and assigned code word sequences of increasing length. All right. We proved the upper bound, saying that the expected length is at most the entropy, and I said that it's also lower bounded by entropy minus some log of function of the entropy. Let's try to prove the lower bound now. Yes.
So that means we can how we got 1 plus mu there in the example.
That requires a proof. All right, that's kind of an exercise, but it's essentially the same set of steps that you followed over here, but you have to do things a little more delicately because you can't choose the distribution to be alpha times 1 minus alpha raised to I minus 1. You have to think about what distribution you would replace q with in order to get this. That's it. All right. Effectively, it just amounts to, in some sense, shifting the distribution, right? Because earlier we had distributions that were supported from 1 up to infinity, but now it's going from 0 up to infinity. And the expectation now has to be taken care of a little carefully because the mean is now no longer greater than or equal to 1. It's greater than or equal to 0. All right? And the probability of something being equal to 0 has to also be taken into account a little carefully. That's it. Right? But yeah, I leave it up to you to find out what this particular quantity corresponds to and how you would modify Q in order to derive this for the whole numbers. Good. Any other questions? Okay. So now what we want to do so we want to show that for any, or let's be particular, for the optimal compression scheme, the expected length is lower bounded by h of xn minus log of e times 1 plus h of xn. Okay. Any questions? Great. And this will involve some concepts that you'll see frequently in information theory. That is, it's not intuitive to see how you prove this lower bound. The upper bound that we proved was kind of very intuitive. It was very natural, right? Because all we did was, okay, what is can we first bound the length of each code word sequence, the ith sequence, that we had the floor of log of I, and then we just made a simple observation that for the ith sequence, the probability is at most 1 over I, and that just gave us the bound. Lower bounds in information theory are in general hard to prove. They require some amount of ingenuity, some creativeness. All right, and that's something we'll see now. So what we want to show is to prove that the expected length is lower bounded by entropy minus something. So what we'll do is we'll introduce an auxiliary random variable. So let me define the random variable L to be the length of the encoding of XL. Right, the length can take any value, any natural number. In fact, it can also take the value 0. So the random variable L can take value 0, 1, 2, 3, all the way up to infinity. Okay. In fact, not that large because we are looking at a finite alphabet. So for a given n, it's bounded from above. So this is a random variable, and I look at the random variable h of xn. I claim that this is equal to, or let me write this as h of xn is equal to h of xn plus h of L given xn. Why can I write this?
Because that is 0, right? H of L given x.
Why is it equal to 0?
Given xn, you know what length was n because you're following optimal scheme.
Correct. So, I mean, it's not just for the optimal scheme. For any scheme, given xn, you know exactly what the encoder does because that's a deterministic function. So, L is a deterministic function of xn. All right. So although L by itself is a random variable, if I tell you what the source is, if I tell you what xn is, L is now a deterministic function of xn. Is a function of xn, we have h of L given xn to be equal to 0. Right? So given xn, there's no more uncertainty left in what the length of the compressed version is. Because you know xn, you know the compressed, you know the encoding, and therefore you know the length of the encoding. Any questions at this point?
Can you repeat once again?
Okay, great. So firstly, when is the entropy equal to 0? When is the entropy of any random variable equal to 0? When the random variable is essentially deterministic, right? So given xn, what can you say about the length of the encoding? I give you the sequence xn, right? How would you find the encoding in the first place? You would basically, you have this table, the lookup table. You would see which row of the lookup table this xn corresponds to, and that gives you the encoding. So the lookup table is given to everybody. You know what the lookup table is. So if you know xn and the lookup table, then you know the encoding. And therefore you know the length of the encoding, which is exactly the random variable L. Right? So given xn, there is no more uncertainty left in L. Right? So L is deterministic given xn. That's why h of L given xn is equal to 0. Is that okay? Great. So this is equal to h of xn comma L, right? Just by the chain rule of entropy. So I introduced a quantity, another quantity as it's sort of a dummy quantity, right? Because it's equal to 0. And this I get using the chain rule. The reason why I introduced this new quantity is because I want to again use the chain rule to expand this in a different form. All right. So this is equal to h of L plus h of xn given L. All right. Remember that L is a deterministic function of xn. So if I tell you only the length, you don't know exactly what xn is, right? You can maybe narrow it down because since you have this table, you know that if the length of the encoding is this, it can only be one of these values, but there's still some uncertainty that is left. So the second term is not exactly equal to 0. And the first term is just h of L, right? Great. So let's call this equation 1 and see how to bound each of these two terms. Okay? Because neither of these terms are what we essentially require. So let's look at h of xn given L. Now this h of xn given L is, I can write this as, again, let's maybe, for the sake of understanding, let's expand this quantity out. Let's see what this exactly is. This is equal to summation over all possible xn, summation over all possible L of pxn L of xn comma L log 1 over Pxn given L of xn given L. All right, which is equal to summation over all L. I'll exchange the order of summation. PL of L times summation over all xn Pxn given L of xn given L log 1 over Pxn given L of xn given L. Right? Nothing much. All I did was I just wrote this joint probability as a product of one of the marginals and the conditional distribution. That's all. And I took the P L of L outside. So this quantity is again an entropy. It's sort of a conditional entropy. It's the entropy of xn conditioned on the event that capital L is equal to small l. So this is equal to summation over all L PL of L of the entropy of xn given the event that L is equal to little l. Okay. Any questions up to this point? Fine. So now if I tell you what small l is, how many possible values can xn take? Remember, we are looking at the optimal compression scheme. It's not any arbitrary scheme. It's the optimal lossless compression scheme. Yeah? It's equal to 2 to the power L, right? Because there are at most 2 to the power L sequences, which 2 to the L source sequences, which have compressed length equal to little l. Can it be less? Exactly. The last, if you look at the last few rows, there could potentially, you may not exhaust all possible code word sequences of length n. All right. Particularly the longest length code words, there may not be 2 to the L of them. There could be fewer because the number of source sequences itself is small. So in any case, the number of such sequences is 2 to the power L, right? So what can you say about this particular entropy? How large can this be? So conditioned on, let's write it down. So conditioned on the event that L equal to little l, xn can take at most two to the L values. All right. So how large can the entropy of xn be conditioned on L equal to little l? So log of the cardinality of the conditional alphabet, which is log of 2 to the L, which is just L, right? Is this okay? I'm using a bunch of properties that we've seen before. Okay, so this quantity h of xn given L right. So you have to be a little careful. The notation can get a little bit confusing because this h of xn given L is a deterministic quantity. It doesn't depend on anything else. But h of xn given L equal to little l is the entropy of xn given a particular event, that L equal to little l, right? So h of xn, what we have essentially shown is that h of xn given L is less than or equal to sum over all L, PL of L times little l, which is just expectation of L, the expected code word length. Right? That's good because now we got one of these terms, h of L. We showed that this is less than or equal to expectation of L. Let's think back about what we want to show eventually. We want to show that to prove this, we already now have two terms. We have this term and this term. So if we are able to show that h of xn given L is less than or equal to log of E times 1 plus h of xn, we are done. Right? So let's try to do that. So now the goal is to bound h of L. Right? And to bound h of L, we are going to use the exercise I just mentioned previously. L is a random variable, right, which takes values 0, 1, 2, 3 all the way up, potentially can go all the way up to infinity, whatever. It's supported over the set of whole numbers. And we know what the expected value of L is. It's equal to expectation of L, the expected code word length. So just using the exercise, this is less than or equal to 1 plus expectation of L times the binary entropy of 1 over 1 plus expectation of L. All right, this is from the exercise. Okay, so now let me expand the quantity I have, the binary entropy. All right, this is equal to 1 plus expectation of L times 1 over 1 plus expectation of L. Let me see. Yep. Log 1 over expectation of L plus 1 plus expectation of L divided by times 1 minus 1 over 1 plus expectation of L log of 1 by 1 minus 1 by expectation of L. Okay, so 1 over 1 plus expectation of L is my P. So it's P log 1 over P plus 1 minus P log 1 over 1 minus P. These cancel. So just simplifying, I get log 1 plus expectation of L plus have 1 plus, so basically this quantity simplifies to 1 plus expectation of L minus 1 divided by 1 plus expectation of L, which is just expectation of L times log of, again, this becomes 1 plus expectation of L divided by expectation of L. So this is log 1 plus expectation of L plus expectation of L log 1 plus 1 over expectation of L. Now I'm just going to make use of a standard inequality which says that x times the natural logarithm of 1 plus 1 over x is less than or equal to 1. For all x greater than 0, or effectively log 1 plus expectation of L plus log e to base 2. Right, so this is equal to log of e times 1 plus expectation of L. Right, this is my h of L is less than or equal to log of e times 1 plus expectation of L. What I want to show is that h of L is less than or equal to log of e times 1 plus entropy of xn. Can I get that from this? Yeah.
E of L is greater than h of x and given L.
Okay.
Then we again use the method h of xn. H of xn is also greater than h of xn given L.
Okay. Something much simpler. We essentially have everything that's required at this point. What did we prove in the beginning, or the other half of the theorem?
H of xn given L is less than equal to
No, not this particular proof, but even earlier in a previous class. What did we show?
Oh yeah, this is upper bounded by entropy.
Yeah, we've already shown that expectation of L for the optimal compression scheme is less than or equal to h of xn. Right? So we just use that. So this basically comes for free from the upper bound of our theorem. Because we earlier showed that the expected length is less than or equal to the entropy. Right. Okay, so now we have an upper bound on h of L. We also have an upper bound on h of xn given L. So h of xn is less than or equal to expectation of L plus log of e times 1 plus h of xn, or expectation, the expected length is greater than or equal to h of xn minus log e times 1 plus h of xn. Any questions? So the proof feels a little bit heavy because you're using a lot of ideas that you've not seen before. But once you get comfortable with the basic results, it will all flow smoothly. All right, and we'll see that it will come naturally because we'll keep repeatedly using some of these techniques. In particular, when proving lower bounds, we'll see that this is a very commonly used approach. You have some particular entropy, you start with some particular entropy, and then you use the chain rule to introduce a new random variable that depends on this somehow, and then again split it again in a different way, again using the chain rule, and then bound each of those terms. All right. This will be the most standard approach to proving lower bounds on some particular metric. All right. Okay. So what we've shown is that for the optimal scheme, the expected length is less than or equal to h of xn, and upper and lower bounded by h of xn minus log e times 1 plus h of xn. Let's try to see what happens for specific sources, right? So what happens if the source is IID? This is also what is called a discrete memoryless source. What is h of xn equal to? Yeah? It's using the chain rule and independence, you get it's equal to sum I equal to 1 to n h of xi, but that is equal to n times the entropy h of px. Okay, that's good. So what happens to the upper and lower bound? So expected length is less than or equal to n times h of px, and it's greater than or equal to n times h of px minus log e times 1 plus n times h of px. Right? Or effectively, if I write this as in terms of the rate, so the rate is n times the expected length. So the rate is just this divided by n. Right? The right hand side is, as n tends to infinity, so if I take the limit as n tends to infinity for both the upper bound as well as the lower bound, this is the upper bound converges to h of px. What happens to the lower bound? Yeah? That also converges to h of px, right? Right? Because I have h of px plus some quantity that grows as log n, right? And that's exactly equal to h of px. So the asymptotic rate is equal to the entropy for a discrete memoryless source. And this is optimal, you can't do any better than this. So R is equal to h of px plus some quantity that decays as log n over n. So as it turns out, this second order term, or the constant in the second order term, is something that has also received a lot of attention. So this is okay, the asymptotic rate is equal to the entropy, and this works fine if you're looking at asymptotic n large enough. But when n is not too large, then the second order terms also start becoming important. Then one needs to think about what is the best possible second order term, or you want to characterize the second order terms as well, and that has also received a lot of attention. Right? One can show that the optimal second order term is essentially the variance. So you can write the entropy as the expectation of log 1 over x, but the optimal second order term is some constant times the variance of log 1 over px. It's called the var entropy. All right. Okay. Any questions so far? Great. So now what happens if I take a Markov chain? Xn is a stationary first order, or let me just generalize to kth order Markov chain. Once again, I'm trying to understand what is the asymptotic rate, the optimal asymptotic compression rate. So remember that a sequence Xn is a kth order Markov chain if Pxn can be written as product I equals k plus 1 up to n of pxi given x1 through x I should write xi xi minus k up to xi minus 1 times pxk of xk, right? This k is something that is small and n is allowed to grow all the way up to infinity. So in this case, what is h of xn equal to?
Summation of I is equal to 1 to k h of n plus
Okay,
summation of I is equal to k plus 1 to n h of I given xi given xi minus 1 xi minus 2 xi minus
correct. So basically, if you can just use the chain rule of entropy, you will get I equal to 1 to n h of xi given x1 up to xi minus 1. This is just by the chain rule. Right? Nothing else except the chain rule. And this is equal to, well, I leave the first k terms as it is. H of xi given x1 up to xi minus 1 plus summation I equal to k plus 1 up to n of h of xi given, now remember, for a kth order Markov chain, the ith symbol depends only on the previous k symbols, nothing else beyond that. So this is xi minus k up to xi minus 1. Moreover, maybe something that I didn't emphasize over here, this is equal to pxk given x1 through, or pxk plus 1 given x1 through xk, right? The distribution of the k plus 1th symbol given the first k symbols is the same as the distribution of the k plus 2nd symbol given the previous k symbols, right? So this is equal to summation I equal to 1 to k. I can write the first summation as simply h of xk, right, plus summation I equal to k plus 1 up to n h of xk plus 1 given x1 up to xk. Right? Because if you take any block of k plus 1 symbols, any contiguous block of k plus 1 symbols, the distribution is the same even if I look at the subsequent block, contiguous block of k plus 1 symbols. Because we assume that it's a stationary kth order Markov chain. So this is nothing but h of xk plus n minus k minus 1 h of xk plus 1 given x1 through xk. Correct. Should be n minus k times h of x k given xk plus 1 given x1 through xk. Right? So if I take the limit as n tends to infinity of h of xn by n, this is nothing but limit n tends to infinity h of xk by n plus 1 minus k over n times h of xk plus 1 given x1 up to xk. So as n tends to infinity, this quantity goes to 0 and this quantity goes to 0. So all that remains is just h of xk plus 1 given x1 through xk. So this quantity, limit as n tends to infinity h of xn by n, is called the entropy rate. And for a kth order Markov chain, the entropy rate just turns out to be h of xk plus 1 given x1 through xk. So plugging in to the upper and lower bounds of the optimal compression rate, we get that the optimal compression rate, or the asymptotic optimal compression rate, is equal to h of xk plus 1 given x1 through xk. All right. So based on this, there's an experiment that you can run. You take a sufficiently large text file, English text file. All right. And you try to compress it using some compression utility like zip. You get some compression rate. So you take the normalized rate, that is the compressed file size divided by the original file size. So you try to compute this particular quantity, and then also try to compute the empirical frequency of occurrence of symbols. All right. So you have, let's say, ASCII characters. If you have if the text file is ASCII, you can find the frequency of occurrence of each ASCII character in that text. Right. And that gives you the empirical probability distribution of that particular text file. So that empirical probability distribution will be a rough estimate of h of x, assuming that this English text sequence or the text file is drawn from a Markov source. All right. Then you can also try to compute the frequency of occurrence of pairs of symbols. Right, consecutive symbols. What is the occurrence of AB? What is the occurrence of AC? What is the occurrence of space A? What is the occurrence of RA? And so on. Right? So you find all frequencies of occurrences of all possible pairs of symbols, and using that you can estimate h of x1, x2, or also h of x2 given x1. Right? So what can you say about h of x1 versus h of x2 given x1? Would you expect one to be bigger than the other, smaller than the other, or you can't say anything? assuming that it's a stationary source. So by definition, what is a stationary source? The distribution doesn't depend on the index, right? So what is h of x1 equal to? Or what is h of x2 equal to? I know h of x1. It's a stationary source. So what is h of x2? H of x2 is equal to h of x1, right? Because it's a stationary source. So this is equal to h of x2. It's also equal to h of x3. It is also equal to h of x4. All of these are going to be the same, all right? Now, and so now for this text file or this stationary source sequence, you have also computed h of x2 given x1, which is also equal to h of x3 given x2, which is equal to h of x4 given x3, and so on. So now what can you say about h of x1 versus h of x2 given x1?
H of x1 is greater than h of
So h of x1 is greater than or equal to h of x2 given x1, right? Okay. So now, so this, I'm sorry, h of x2 given x1.
Isn't it 0?
Why?
You know that h of x2 is equal to h of x3. By saying h of x is equal to h of x1 plus h of x2.
there is a joint of both of them.
That is h of x1 comma x2 is equal to h of x2 given x1 plus h of x1, right? It's the joint entropy which is equal to the sum of h of x1 and h of x2 given x1, but h of x2 is not equal to h of x2 comma x1. Which one? Oh, this? By the fact that conditioning cannot increase entropy. Conditioning only reduces the entropy. So I've used the fact that h of x1 is equal to h of x2. So what can you say about h of x2 versus h of x2 given x1? I have not proved it yet. I totally agree with that, and we'll prove that in just a little bit. But assuming that that is true, assuming that that property is true, you agree that h of x1 is greater than or equal to h of x2 given x1. Right? Valid point. I still have to prove that conditioning can only reduce entropy. Right? But assuming that is true, this should happen. Right? So h of x1 is greater than or equal to h of x2 given x1. You can run this experiment, take a large enough text file, compute the empirical frequencies of pairs, and compute the corresponding entropy. You will see that h of x1 is greater than or equal to h of x2 given x1. Now again, I can look at triples, all possible sequences of 3 contiguous symbols, find the frequency of occurrences of all of these, and then estimate h of x3 given x1, x2, right? Yeah.
How can we conclude that h of x2 is equal to h of x1?
Let's assume, again, it's assuming that the source is a stationary sequence, right? We're assuming that it's a stationary source, which is reasonable to expect in practice. One way of doing this is you take the whole sequence, right, the whole text, you divide it into 2 blocks. And for each block, you compute the frequency of occurrence of symbols. You'll see that the frequencies will be roughly the same as long as n is large enough. Right. So you take any piece of text, a large enough piece of English text, you'll see that the frequencies of occurrences of all of the characters will be roughly the same. Right. And all of this we're doing approximately. I can't say that the entropy is exactly equal to what I get based on the frequency, but it is close. Okay. So I can, as I said, I can now compute frequencies of triples and compute h of x3 given x1, x2, and So this will be greater than or equal to this, and so on. I can keep doing this, h of x4 given x1, x2, x3, and so on. Now if you have a large enough piece of text, you'll see that there's going to be a big jump between h of x1 and h of x2 given x1, and maybe h of x2 given x1 and h of x3 given x1, x2. But after a certain point, you'll see that the entropies will be roughly the same. No more amount of increasing the history is going to improve or increase the or cause a significant decrease in the conditional entropy. All right, and you will also see that that particular quantity will be very close to the compression length or the compression rate that you get using zip. All right, for all of this to happen, you need like a really large body of text. But even if you take, let's say, a megabyte or so and try to do this and compare it with even the empirical frequency and pairs of symbols, h of x2 given x1, you'll see that they're reasonably close. They're not too far away. The compression rate that you get using zip and what you get for h of x2 given x1 or h of x3 given x1, x2 will be close. Right? So there's strong empirical evidence to suggest that text drawn from any reasonable language like English actually behaves like a stationary source. In fact, something more, it behaves like a stationary and ergodic source. All right? Any question? Okay, so now I'll define a quantity called the mutual information, because remember, I want to prove that conditioning cannot increase entropy, conditioning can only reduce entropy, right? We have essentially all that we require. All that we need is essentially just another definition. So the mutual information for a pair of random variables x comma y, which I'll denote I x semicolon y, is the KL divergence between the joint distribution between x and y and the product of the marginals px times py. Right? So basically, this is the distribution of x comma y, taking into account the correlation between x and y. And this would be the distribution between x and y, assuming that x and y were independent but have the same marginals. Right? So the divergence between these two distributions is just the mutual information. All right? So in other words, the mutual information is, loosely speaking, trying to measure how far is the joint distribution being away from being independent. All right? So it measures distance to independence between random variables. If random variables are very close to being almost independent, then the mutual information would be small. If there's a lot of correlation between x and y, then the mutual information will be large. So this is equal to sum overall x comma y pxy of xy log pxy of x comma y by px of x py of y, which is also equal to sum overall xy pxy of x comma y log px given y of x given y by Px of x. Right? Now I'll split this into two terms. Sum overall xy, Pxy of xy, log Px given y of x given y plus sum overall xy, Pxy of x comma y, log 1 over Px of x. What is the first term equal to? This is just h of x given y, or the negative of h of x given y. What is the second term equal to? It's equal to h of x because I can marginalize y out. I get summation over all x, Px of x log 1 over Px of x. Right? So this is nothing but plus h of x. Right? So the mutual information is equal to h of x minus h of x given y. And again, here in this particular step, I sort of got rid of y, but if I got rid of x, I could show that this is also equal to h of y minus h of y given x. Alright, so it's a symmetric function in x and y, loosely speaking, because it's not really a function of x and y. Alright. Now I know that the mutual information is basically a KL divergence, and KL divergences are greater than or equal to 0. Right? So the mutual information is also greater than or equal to 0. And this basically implies that h of x minus h of x given y is greater than or equal to 0, or h of x is greater than or equal to h of x given y. So this gives us the inequality that we were looking for, which is that conditioning can only reduce entropy. Any questions? Okay. So we've seen sort of the non-negativity properties of each of these three quantities, the entropy, the KL divergence, and the mutual information. We've seen that all these three quantities for discrete random variables, they're all non-negative. Now let's also try to see the convexity or concavity properties of these quantities, right? So the property is that the KL divergence is convex in the pair P comma Q. What does this mean? It means that if I take a PMF PQ, and if I take another PMF P prime Q prime, and any alpha between 0 and 1, then the KL divergence between the distribution alpha P plus 1 minus alpha P prime and alpha Q plus 1 minus alpha Q prime is going to be less than or equal to alpha times the KL divergence between PQ plus 1 minus alpha times the KL divergence between P prime and Q prime. This is just definition of the KL divergence. Questions? Okay, let's prove this. This is fairly straightforward, nothing very complicated, just almost directly follows from the log sum inequality. So let's write down the left hand side if we want, or let's try to do something even simpler. So let's fix one particular x in the alphabet, okay, and look at the quantity alpha times p of x plus 1 minus alpha times p prime of x log alpha times p of x plus 1 minus alpha p prime of x divided by alpha q of x plus 1 minus alpha q prime of x. This is the form, let me use a different notation. So this is the form, say u1 plus u2 log u1 plus u2 divided by v1 plus v2, which by the log sum inequality, all of these are non-negative quantities. So by the log sum inequality, we know that this is less than or equal to u1 log u1 by v1 plus u2 log u2 by v2. I'm sorry, which one? Yep. Okay. Correct. Yes. So effectively, I could just replace 1 minus alpha with some beta greater than 0. Oh, different. Well, that won't really help. We'll just see the next step in the proof. So this quantity that I had over here, this is less than or equal to alpha p of x log alpha p of x by alpha q of x plus 1 minus alpha p of x log 1 minus alpha p prime of x, I'm sorry, this should be p prime, divided by 1 minus alpha q prime of x. Right, and crucially, these alphas and these 1 minus alphas cancel out. Right. So I want the same alpha for both p as well as q, and p prime as well. Whatever comes for p prime should also come for q prime. Right, so this is equal to alpha times p of x log p of x by q of x plus 1 minus alpha p prime of x log p prime of x by q prime of x. If I sum over all possible x, the left hand side is nothing but the KL divergence between alpha p plus 1 minus alpha p prime and alpha q plus 1 minus alpha q prime. Whereas the right hand side is alpha times the KL divergence between p and q plus 1 minus alpha times the KL divergence between p prime and q prime. All right, so that just completes the proof. All right. Any questions? Yeah.
Logs and you got is a vector side.
Correct. So this in this case you treat this as a vector of length 2. So you have u and you have v. Right, I can take any number of symbols. In this case I just take 2 symbols. That's enough. So this proves that the KL divergence is convex in P and Q, but it also gives us some derivative results automatically. We know that the KL divergence between Px and the uniform distribution is equal to log cardinality of x minus the entropy of Px. Since the KL divergence is a convex function, so now if I view this as a function of Px, then this quantity is a convex function of Px. So this is a convex function of Px, which must mean that h of Px is a concave function of Px. And again, using essentially the same ideas, you can prove that the mutual information is, now this is a function that depends on the joint distribution Pxy. So of course I can think of it as a convex function of Pxy, but what we'll be frequently interested in is you fix Px and look at it as a function of Py given x, or you fix Py given x and look at it as a function of Px. Right? So we can view this as some function of Pxy, or equivalently some function of Px as well as Py given x. Because if I specify Px and I specify Py given x, it automatically tells you what the mutual information should be. Alright? So this is, so if I write the mutual information as a function of Px and Py given x, this is a convex function of Py given x for fixed Px, and it's a concave function of Px if I fix Py given x. The advantage of doing this, as we'll see later on, is that for a given Py given x, I can use any convex programming approach to maximize the mutual information with respect to Px. And likewise, for a given Px, I can try to minimize the mutual information between x and y with respect to Py given x using any convex optimization technique. All right. So we have a wide array of tools in convex optimization to solve these problems. At present, we don't know why we would like to maximize or minimize the mutual information, but we'll see that this will naturally arise later on. All right. Question.
Y given x or 6 given
Y given x.
y given.
Yes. So it's a concave function of Px if I fix Py given x. It's a convex function of Py given x if I fix Px. because py given x and px specify pxy completely, right?